Hey folks, in this video we're talking about heat flow and how that affects conservation of energy, or I guess how conservation of energy affects heat flow. More flow than you know! Let's go! We got a few objectives here. I want you to be able to explain how heat flows between different substances and explain how the law of conservation of energy and how it relates to heat flow. So heat flow, that's when thermal energy flows between substances. Like if I've got a cold glass of water in a hot room, the heat is going to flow from the room into my cold water. And so yeah, energy flows from a substance at a higher temperature to a substance at a lower temperature. Hot room flows into cold glass. Other examples, if I've got hot metal and I put that in cold water, well, the heat's going to flow from the metal into that water. The energy that the metal loses is gained by the water. So there's no energy being destroyed or lost. It is just moving from the metal into that water. For example, if you've got an ice cube and you pop that into some warm water to cool it down, well, now the heat is going to flow from that water to the ice. The water is at a higher temperature, so heat is going to flow from the water into that ice, and it's going to make that water cool down. Energy that is lost by the water is gained by that ice, and that's why that ice will eventually melt. Or if you put your foot on some hot sand, heat is going to flow from the sand, which is a higher temperature, into your foot, and that's going to make your foot feel uncomfortable as it gains energy. Yeah, neat. So conservation of energy. Well, we've talked about conserving stuff before, like matter. Energy is also something that gets conserved. We can neither create nor destroy energy. It can only change forms or move between substances. For instance, I could take electrical energy and convert that to chemical energy. Or I could take something, like in those previous examples, and move heat between, or thermal energy between substances. I can move charge, electric energy between things. Energy. I can move it around, can't destroy it. So when we conserve energy in heat flow, when there is heat flow between two substances, heat gained / lost by each substance is equal but opposite. So whatever gets cooled down, the Q, or heat that it changed for it, or heat flow for it, is going to be negative. And that's going to be equal, the number is going to be equal to the heat gained by whatever's being heated up. Let's look at an example. Put some iron in some cold water. If the iron loses 500 joules of heat, it'll have a negative Q. The water is going to gain that same amount, 500 joules of heat. So Q for the iron is negative 500 joules. Q for the water should be positive 500 joules. The water is heated. It gains 500 joules. The iron loses that exact same amount of energy because I got to conserve energy. I can only move it from my iron into the water. And so we can see that negative Q for iron equals Q for water. Nifty! So we can use this to do some spicy boy problems. Wow. Let's look at one of these right now. So I'm going to solve this problem by knowing that Q for whatever is heated is equal to negative Q for what is cooled. So why don't you read over the problem and see if you can think about how to approach this. And then we'll do it together. Cool. Well, you paused the video and looked over this. When I approach this problem, I know that we're talking about both iron and hot sand. So what I'm going to do is I'm going to set up a list of variables for iron and also stuff for sand, because they are both important for this. So I'm going to read through the problem and see what information I can fill in here. Well, for this whole problem, there's no mention of joules, kilojoules, anything about actual energy. So I'm going to say I don't know the heat flow. However, I do know the mass of the iron, and I know the specific heat of the iron. I do not know the change in temperature for the iron. We want to find the final temperature. We know the initial temperature, so we can write down that part of it. Because remember, delta T is equal to the final temperature minus the initial temperature. So I know whatever TF is, that minus 15 degrees C is delta T. Cool. And so I'll do the same thing for sand. I don't know what Q is. I do know the mass, though. I do know the specific heat. And similarly, I don't know the final temperature, but I know the initial temperature. Well, I don't have three complete variables for either the iron or the sand. So independently, I can't really do anything with these, plugging them into this equation. But what I can do is write down what I do know already, all the variables I know, the iron and the sand. And I can say to myself, well, Q for that iron, this whole magooger here, is going to be equal to the negative Q sand. The sand is getting cooled down because that iron is getting heated up by it. So I could put all this in for Q of iron, and I could put all of this in for my Q sand. And that is exactly what I'm going to do. And I'm going to make sure that I keep that negative sign in the mix. Well, what I'm going to do next is I'm going to simplify these terms, I guess. Yeah, so I'll do 25 times 0.45, give me this number, and I'm going to drop most of my units at this point just for convenience in writing things out. I will reintroduce them later. And I'll also do negative 50 times this dude, 0.83, simplify them to that. Well, now what I can do next is expand or why can't I say this? Distribute this into my parentheses. So I will distribute this negative 41.5 into these parentheses and this 11.25 into these parentheses. So that'll give me this new equation, 11.25 TF minus whatever 11.25 times 15 is. What's that number? 168.75. And I'll do the same thing and distribute into the parentheses on the other side, making sure that I'm careful about this negative sign. Cool. Well, now what I'm going to do is consolidate my like terms. So I'll bring this TF over to here. I'll add 41.5 TF to both sides. Neat. Then I'll add 168.75 to both sides. So this is gone from here. That gives me 57.75 TF. The final temperature equals 16,768.75. Well, I can divide each side by this number, my 52.75. I don't want to know what the value of 52.75 TFs is. Just one TF. So that gives me final temperature. Sweet sauce. So that was an example of how we can do some spicy void problems combining systems of equations using our knowledge of conservation of energy. Sweet stuff. I hope you found that to be pretty logical. And that's the end of this video. I hope you enjoyed it. I hope you understand a little bit more about how heat flows between objects and how that energy is neither created nor destroyed. And also how we can use the knowledge of conservation of energy to do some math with our favorite equation, Q equals mc delta T. Great. Well, that's the end of this video. Ta-ta. I hope you have a great rest of your life.